All right, let's start. So this is the last chapter that we will study. I mean the big chapter, which is about the orthogonality. And this orthogonality is related to the vectors being perpendicular to each other, having like 90 degrees, right? And then if the two vectors v1 and v2 have the angle of 90 degree, and then their inner product should be 0. Okay, so this is the main kind of ingredient or property that we focus on throughout this chapter. Okay, and then using this orthogonality things, so this something called the least squares is about solving the linear system even when we don't have the even when we cannot find the exact solution of our given linear system. So I think I mentioned about this in the first class of our semester. So so given ax equals b, which is our linear system, and then we have the solution may exist or not, right? So in case solution doesn't exist, we want to be able to find the approximate solution. Okay, so in that case, even if we cannot satisfy all these given equations, we can just we try to satisfy those equations as much as possible, even though it is not an accurate solution. Okay, so we utilize this orthogonality thing in order to find some approximate solution of this given linear system. Okay, so let's start with this definition of the inner product. Okay, so we consider the two vectors living in the same dimensions, which is Rn in this case, and then we can consider each of these vectors as n by 1 matrix, which are just the column vectors. And then so we think of this situation in R3. So suppose u is given as this and v is given as this, and then this one can be represented as this guy because it's just a 3-dimensional vector, but also it can be represented as R3 by 1, which view our vector as a matrix. And then we think of it's a transpose version, which is our row vector. Okay, and then this row vector or this horizontal kind of matrix, and it's a product or matrix multiplication with the original matrix, and it can be written as U transpose V. Okay, so this is the definition of this inner product between U and V. Okay, so this kind of a little thick dot is representing the inner product operation. Okay, and this guy is the kind of matrix multiplication. Okay, so you can view you can understand this thick dot as a special kind of operator between vectors. So we have a addition, subtraction, and and these kind of operations, and then we are now learning a new operation denoted by this thick dot. So it's like this: 1, 2, 3, and 4, 5, 6 is defined by so this is a U and V, and it is the same as U transpose V, and thus 1, 2, 3, and 4, 5, 6. Okay, so this is just a matrix multiplication, okay, between this row vector on the left and the column vector on the right. And so in this case, one thing that we need to be careful about is, suppose we consider this a matrix multiplication of A, B. Yeah, so A is some matrix and B is another matrix, but we shouldn't use or we shouldn't write A dot B, right? Because this dot is no longer just a plain multiplication. It now has a special meaning of the inner product between the vectors, right? So this is wrong representation, at least in the matrix world or linear algebra. Okay, so this is called the inner product, and also it's called the dot product. Okay, and then in general, if we have these two vectors with this dot operator or dot product, it's represented as this matrix multiplication, and then it is defined by this, right? So in the previous case, this guy is 1 times 4 plus 2 times 5 plus 3 times 6. Okay, so we know this quite well. And then let's look at some properties of this inner product. Okay, so this inner product satisfies this commutative law, right? So if we change the order between these two vectors, they are the same. And then it is also satisfying this kind of distributable law when we first compute this sum of these two vectors, and then it's the inner product with another vector, and then it is just distributed in this form, and then the scalar multiple of a first vector times the inner product with another vector can be represented by this. Okay, and then we can freely move the C into the second vector. And then let's look at the last one. Is considering the inner product with the same vector u dot u. Okay, so in this case, like 1, 2, 3, and then we consider the inner product with the same vector, and then you guys see that this is computed always as the sum of the squared values. So it is always greater than or equal to 0. And when does it equal to 0? It is when your vector is all having all zeros, right? So this is the only case that we obtain 0 inner product value. Okay. Okay, and then by combining B and C, we can represent or obtain the last property. So let's think of this operation or understand this property. So given some multiple vectors, we first consider its linear combination, and then we perform the inner product with that linear combination with another vector w, and then that is the same as the case where we first compute the inner product with each of our ingredient or basis vector with the vector on the right, okay, and then linearly combine them by using the same linear combination weights. Okay, so it can be viewed as like this dot product. From the perspective of this linear transformation thing, this dot product can be viewed as a kind of linear kind of transformation that satisfies this kind of relationship where we first do the linear combination and then do this operation later, and that is the same as the case that we do the inner product first and then linear combination after that. Okay. Okay, and then focusing on this item D, this guy, the inner product with the same vector, that is called the length or the norm of our given vector. So so that has the special notation for it. So it is like, given this vector, its norm or the length of this vector is represented by this double bar on the left and the right, and then that is the same as so 1 2 3 and 1 2 3, and it is 1 squared plus 2 squared and 3 squared, right? Okay, and then if we compute this as squares, and then we can write this one, right? So physically this has the meaning of the length of the vector, right? So vector has the direction and the length, and then the vector has the length of this value. Okay, and then looking at this equation is sometimes quite useful, and so it can change the norm or the length operator of a given vector into a inner product between the same vector, and then this inner product can also be represented as the length of the single vector. Okay, so we will and sometimes this property will be used quite importantly in order to prove some meaningful properties. Okay, and when thinking of the length of the scalar multiple of a given vector, so it is the same as the scalar multiple. I mean, it's the absolute value times this the original vector length. Okay. So so let's think of this thing, 3, 4, and then what is the length of this vector? It's 5, right? Based on our Pythagorean theorem, and then using the norm operator that we studied, it is 5, right? And then let's think of this thing. So this thing is 3, 4 and 6, 8, and this 6, 8, it is so it is just 2 times 3, 4, right? And then it is like 2 times 3, 4, and so 2 times 5 equals 10. So if the original vector length was 5, and then the scalar multiple of that vector, and if we compute the length of it, and then we first compute the length of the original vector, and then we change, or we just multiply its length by using that scalar vector multiplied with the original vector. Okay, so it has this representation. So that means if we do the scalar multiple of the given vector, and then of course it will not change the direction of the vector, but it will only change the length, right? And then how about changing the length of the original vector as just 1? Okay, so in this case the vector length is 5, but suppose we want to obtain the vector that has the same direction. So direction didn't change, but we want to just change the vector length as 1. Okay, so how do we do that? So in this case the vector length is 5, and so we consider this 1 over 5. Okay, 1 over 5 times 3, 4. Okay, so in this case, the vector length will be changed into 1, right? And then the direction will not change at all. So this guy can be viewed as, can be written as this guy. V times, 1 over, the norm of V, right? So this guy, will have the same direction, and the length will be changed into 1. So okay, so that vector is called the unit vector. So that means, the unit means that the vector length is just 1. And this process of making a given vector a unit vector, okay? So changing like 3, 4 into like this vector. So that is called the normalizing the given vector V. Okay, so given this 4-dimensional vector, we can compute its unit vector that has the same direction, and the length has now changed into 1. Okay, so we learned the notion of the vector length as the norm, right? Given this vector, right? And then how about the distance between the two vectors? So we now consider the two vectors, u and v, and the distance between these two vectors. So basically, see. So if we are given these two vectors, v and u, so the first vector is this guy, and the second vector is this guy. Okay, and then we now consider the length of those 2 points, or the distance between those 2 points. Okay. Okay, so that is represented as distance of u comma v, or v comma u. It is the same. And that is actually computed the norm of, or the length of, the difference vector between the two. Okay. So this guy is again a single vector. Okay. And this dist function will take the input as these two vectors. Okay, so let's draw this single vector. So that vector is this guy. So u and so basically u plus and minus v. So we have u here, and what about minus or negative v? Negative v is this guy, right? And then we consider this parallelogram, right? And then this guy, okay? This vector, this vector is corresponding to this guy, and then we consider the length of it, right? And that length is the same as this distance between the 2 points. Okay. Okay. So although it's it looks quite obvious, but the distance between the two vectors are defined as the norm of the single vector, which is represented as this u minus v. Okay, and then now let's think of this orthogonal vectors. So this orthogonal is the same as perpendicular, right? That has the 90 degrees between the two vectors. So although this figure doesn't look right, but if we have this vector u and v, and then we consider the situation that this two vector angle is 90 degree, okay? And then if we think of this triangle, okay, and then the distance between these two vectors and the distance between these two vectors will be the same if they have the angle of 90 degrees over here, because we have also a 90 degrees on this side, right? And so two triangle of like this thing, okay, this thing and this thing, okay, the left and the right triangle are the same one, okay, and so the lengths between this guy and this guy will be the same, right? So this is u and this is v and this is negative v, okay, so the lengths for this part will be represented as this and this, so they will be the same because the two triangles are the same. Okay, and then let's just equate these two elements, okay, and then just develop or just evaluate these two equations. So we want to make these two guys as the same, but yeah, so it's like u and minus v and the norm operator. So that is the definition of the distance between the two vectors. And then we have u plus v, right? And then we now change this norm operator into the inner product, like u and v, u plus v and u plus v, right? So we now utilized this thing. It's the same as the square root of the inner product of the same vector, right? But because this square root, yeah, it is not easy to handle this equation. So let's just consider it's a squared version, okay, squared version, and then we can remove this square root factor, and then we now consider the inner product between these two vectors. And then yeah, we studied that this inner product is this satisfying this distributable law, and then we can represent it as this, and then this guy is converted into the vector length of u and the vector length of v. And what about these two guys? So they are the same thing because this inner product is commutative, right? And thus they are the same, and so we can represent it as 2 times u dot v. So that was this guy, which is corresponding to this this part. And then what about this guy? Yeah, so this guy can be similarly evaluated and then rewritten in this form. And so this part and this part should be the same, and thus this part and this part, yeah, should be the same because they are canceling out with each other. And so yeah, by equating these two, we obtain this 4 times u dot v equals 0. Okay, and so we obtain u dot v equals 0. Okay, so what we did here was that if we have a 90 degree over here between these two vectors, and then we can form these two kind of triangle on the left and the right, and they will be the same, and thus those two lengths of the line segments from these two triangles should be the same, and that gives this kind of conclusion that the inner product between the two vectors should be equal to 0. Okay, so when the two vectors have the 0 as an inner product, and then we call them as an orthogonal vector. Okay, and then let's look at some special case where we have a 0 vector between the two. So yeah, between the two, suppose one vector is 0 vector, and then yeah, we always obtain the inner product as 0. And so we can think of this 0 vector is orthogonal to any vector in the same space. And yeah, if the two vectors are orthogonal, and then this guy, yeah, is represented as this guy plus 2 times u dot v, right? Because this guy was what? This between u and minus v, right? And this guy was found over here, right? And now, if we assume that these two vectors are orthogonal, and then this part should be 0 from this property, right? And then, yeah, so we obtain this, right? And so, yeah, this one is called the Pythagorean theorem, okay, that we already know. Okay, and then the next thing is about this orthogonal complement. And so, yeah, I think we studied this already, so I will just skip this part, okay? But so this orthogonal complement is just considering like the two subspace. So given the subspace W, okay, in maybe R5, okay, and then we consider W, no, not W transpose, W perpendicular, okay, so this is called the orthogonal complement, okay, so these are living in the same space, and the definition of this orthogonal complement is that we just pick up one vector from W and another vector from W perpendicular, and then for any vector of W, any vector of U and V, these U dot V should be equal to 0, which means that, yeah, for whatever chosen two vectors from W and W perpendicular, they are always perpendicular to each other or orthogonal to each other, or their inner product should be always 0. Okay, and yeah, just to remind you guys, suppose W is basically the span of columns of A, okay? So basically we consider the column space of an A. So suppose W is column space of an A, okay? And then what is this null space of an A? The orthogonal complement. So this is basically the null space of what? A transpose, right? So this is what we studied previously. So if A has maybe 3 columns, okay, and then A1, A2, A3, and then W is basically span of A1, A2, A3. Yeah, this is just directly obtained from the definition of the subspace or this column space of an A. Okay, and then what about W transpose? I mean the W perpendicular. And then in that case, such a vector. So let's call this vector V. And then what kind of conditions or requirements do we need to satisfy? Okay, so this guy should be this guy, and this guy, right? So let me just point out the high level story again. So you guys know the definition of the W perpendicular or orthogonal complement. I mean, so we consider another subspace. So starting point is like, so we start with this given entire universe as maybe R5, and then we consider some subspace W, and then suppose that is a column space of matrix A, And then what about its orthogonal complement, which means that we pick up any vector from W and then another vector, any vector from W perpendicular, and then they should be always orthogonal to each other, which means that they should their inner product should be always 0. Okay. So U and V should be always having a 0 as an inner product. Okay, so this single requirement or this single equation is actually the same as this thing. So if we want to satisfy this equation, and then so U is any vector from W. So U can be represented as maybe some linear combination of maybe C1, A1, and C2, A2, plus C3, A3, right? So this is the form of a linear combination of A1, A2, A3, right? And then what about this V matrix that is orthogonal to any vector U that is a linear combination of A1, A2, A3? And then if the V vector satisfies these three equations separately, and then it will be just necessary and the sufficient condition that satisfies this equation for any vector U in W. Okay, so that means V should be orthogonal to A1 and A2 and A3, right? And so please pay attention to this kind of form, because we will utilize this kind of thing in the least squares kind of chapter. So let's just rewrite it. Okay, I'm gonna just rewrite these three equations into this form. A1 V equals 0, A2 equals, so I just changed the order between the two vectors, and then let me just write it in this form. A1 transpose V equals 0, A2 transpose equals, right? So I just changed this dot product into this matrix multiplication. Okay, then so this is like this A1 transpose, and then this vector V, and we have the same vector V on the right, and then we have these three row vector, right? And then what about single matrix? What about forming the single matrix equation? It is like A1 transpose, A2 transpose, A3 transpose. Okay, so we just formed the single matrix, okay, by collecting just these three row vector, and then just multiply V on the right, and then they will be 0 and 0 and 0. We just change it, these three equations, into a matrix equation form. Matrix equation form. Okay, so this guy is just written as A transpose V equals 0, right? And this is what? This is, what is the collection of all the possible vector of V? So that is called the null space of A transpose, right? Because that is the definition of the null space. Okay. So that way, this column space of an A is, the perpendicular, the orthogonal complement of the column space of an A is the null space of A transpose. Okay. And this W perpendicular is also the subspace, which means that it is spanned by some vectors, right? And so we can find the basis vector. And how do we find the basis vector? So we basically solve this A transpose B equals 0 by just doing the row reduction and then find out the parametric vector form, right? So that's how we obtain the basis vector for this double perpendicular. Okay, so that was about this. So yeah, the proof is exactly the same as what I described in this slide. So you can briefly check. Yeah, after the class. So okay, and then although it's an optional thing. But yeah, I'm not gonna prove this, but let me just point out some meaningful part as a way to utilize this inner product. So you guys know that this inner product between these two vectors are, I mean, we are not considering the orthogonal vectors. So we are just considering like these two vectors having some arbitrary angle, right? And in this case, it is written as this guy. Where the theta is the angle between the two vectors. Have you guys studied this property? 이거 고등학교 때 배웠죠? 네? Do you know how to prove that? So the proof is done by I don't know how to say it in English, but 뭐 코사인 제1법칙, 코사인 제2법칙, 그다음에 사인 법칙 뭐 이런 거 있잖아요. 이거는 이제 코사인 제2법칙으로 유도가 돼요. 네, 뭐 하여튼 우리 중고등학교가 아니라 대학교라 코사인 제1, 2법칙은 스킵하는 걸로 하고. 네. Okay, so yeah, you don't need to actually. Yeah, you don't need to study how to prove it because it's out of the scope of this class. But yeah, it's just quite meaningful and it's a quite useful property that is actively used in many interesting data mining and analysis and machine learning and artificial intelligence problems because this cosine theta is represented as this guy. Right, and so in this case, we can always compute the cosine theta between the two vectors, and then this cosine theta is having the range from -1 through 1, right? And then if they have, so if the angle is 0, and then what is the corresponding cosine value? So cosine value will be 1, and then if the two vectors are having a 90 degrees, and then the cosine theta or cosine 90 degree will be 0. So I mean this cosine theta is sometimes called this cosine similarity, or the similarity between the two vector u and v, and that means how similar these two vectors are, and we measure the similarity between the two vectors as the cosine theta between the two vectors. Okay, so let me just give one example. Let me just try to find. Okay, this is just a simple example. So given these two-dimensional space, u, 1 and 1, 3, and then suppose we want to compute the cosine theta, where the theta is the angle between the two vectors. And then we first compute the inner product, and then please note that we have a thick dot here, but we don't have a dot here, right? So you shouldn't put the dot here because it's just a matrix multiplication, right? Okay, then we separately compute the vector lengths of these two. So the length or the norm of first vector and the second vector, and then we just equate the inner product with the product between the norms of these two vectors times cosine theta. And then this cosine theta is obtained 1 over square 2, and thus we can obtain this theta as 45 degrees. Okay. And that's it for first chapter. And then let's move on to the second chapter. Before moving on, is there any questions? Yep, so far it's quite obvious and quite easy. And then let's move on to the second chapter of the orthogonal set. Okay, so in the case of an orthogonal set, we consider a set of vectors are given, where all the vectors are living in this Rn. Okay, and we want to determine whether these given vectors are orthogonal set or not. Okay, and then what is the definition of this orthogonal set? So given these multiple vectors in a set, so we just pick up any two vectors from our set, and then if their inner product between the two is always 0, and then this is called the orthogonal set. And basically it means that, suppose we are given like three vectors in our vector set, and then for any given two vectors, okay, and their angle is always having a 90 degree. Okay, so that is the definition of this orthogonal set. Okay, and then intuitively, this orthogonal set is quite related to the linearly independent set. So given these three vectors, so we also studied whether these vector set composed of these three vectors are linearly independent or not, right? So between the two conditions of like a set being linearly independent and the same set being orthogonal, okay? So between these two conditions, orthogonal set is much more strict condition. So that means given the three vectors, suppose these three vectors are linearly independent, okay? And then they may or may not be orthogonal, of course, because like this, having a little bit of a kind of angle less than 90 degrees, right? In this case, these three are linearly independent. And how do we check? I mean, we know it very well. So the first and the second, and the span, and the third is outside of our span of the previous two. And so these three are linearly independent set. But in this case, of course, the angle is not a 90 degree, and thus their inner product will not be 0. But suppose these three vectors are orthogonal to each other. I mean, they are orthogonal set, and then they are automatically be linearly independent. So in this case, the first vector, let's check whether they are linearly independent or not. So they have an angle like between the two, we have a 90 degree, right? And then like the span of the previous two vectors will be formed like this, and then the third vector is basically outside of this plane, and that means, so if this vector is linearly independent, and then this vector should be inside of our span of the previous two vectors, right? So in that case, the angle cannot be 90 degrees. Okay, so we will see this situation in a little bit more detail in the later part. Okay, and then this is the intuition that we want to keep in our mind, but the proof of this theorem is quite easy. Okay, so let's just prove it mechanically without not much of without much of our spirit or intuition. Okay, so okay, so it is saying that if the set is orthogonal and then they are automatically linearly independent, and then it means that, yes, in order to prove that, let's just consider just the opposite situation by negating this conclusion that, what if they are linearly dependent? Okay, what if the vectors are linearly dependent? And then we want to check whether it is possible that these sets are, this vector set is orthogonal or not. Okay, so if the vectors are linearly dependent, and then this one is a homogeneous linear system, and then we should be able to find some non-trivial solution for it, right? And so those linear combination coefficients should be non-zero. I mean, for at least 1 and 3. But from here, let's just multiply. Okay, so this is a kind of a typo here. So it is a thick 0 because it's a 0 vector. Okay, and then let's just do the inner product with these two sides of a vector with the first vector u1, given in our original set here. Okay, and then 0 vector dot u1, and then the linear combination that we obtained here, this is a u1. Okay, and then this guy can be distributed in this manner, and then this guy is the vector. Okay, I mean the inner product between the same vector, and then we obtain these. And then by definition of this orthogonal set, these parts will all be 0, because between any two vectors that we chose from the vector set, by the definition of being orthogonal set, they should be, their inner product should be 0, and thus we obtain this, right? Okay, so 0 times u1 will be 0, right? The inner product with the 0 vector will be always 0, and thus, we obtain c1 being 0. So I forgot the one thing over here. So we consider this orthogonal set composed of all the non-zero vectors. So if our vector set contains a 0 vector, and then this is automatically a linearly dependent set. We know that, right? Because if we have a 0 vector, and then maybe this vector, and then we can always find the non-trivial solution for this equation by setting C1 as non-zero and C2 as 0, right? So that way we know that the 0 vector is contained in our vector set, and then this is linearly dependent set. Okay, so we just exclude this case, so that our orthogonal set is composed of non-zero vectors. Okay, so non-zero vector is what? The vector length or the inner product with the same vector will be non-zero, and so this inner product value can be divided safely from each side of our equation, and thus we obtain C1 being C1 as 0. Okay, and then we can also do the exact same thing by just multiplying u2 in the place of u1, and then this guy is u2, and then we obtain C2 is also equal to 0, and C3 and so on, and then we obtain our conclusion is that C1 through CP are all 0. Okay, that means in this equation, the linear combination coefficient, each of our linear combination coefficients should be all 0, and thus we cannot. It means that we shouldn't be able to find any non-trivial solution in this case, right? So we cannot find any non-trivial solution, and thus the set is always linearly independent. Okay, then and then let's now consider a subspace W spanned by some vector, or the subspace W that has the basis vector as some vector. Okay, for example, W is span of 1, 2, 3, and 4, 5, 6, and these two vectors are linearly independent, and thus the basis of the subspace is just these two vectors. And then what about the basis vectors are orthogonal? Okay, for example, 1, 2, 3, and then 4, 5, what? So what is this value? So it is just a value that makes the inner product between these two as 0, right? And so 4 and so this value is this guy. Okay, so in this case these two vectors are orthogonal to each other. And then what about the span of these two vectors? Okay, and then if we have a vector subspace W, and then if we can find, our basis vectors are orthogonal set. Okay, and that is called the orthogonal basis of a subspace. Okay, and so in the latter part that we will study, given a subspace, given a particular subspace, we want to find the basis vector for our subspace. So let me just give an example. So suppose we consider this a column space of an A, and the A is like 1, 2, 3, 4, 5, 6, and maybe 3, 3, 3. Okay, so we have these three columns. Okay, and then this guy, so we keep adding one vector at a time into our basis of this column space of an A. So the first vector 1, 2, 3, and the 4, 5, 6 is still a linearly independent, and that's the valid another valid basis vector. And then what about 3, 3, 3? So 3, 3, 3 is basically V1 and V2. This guy is V2 minus V1, and thus that is included in the span of the previous two, and thus the basis will be just two of these, the first two vector, right? And then let me ask the question here. The basis, so basis of so this is the basis vector of this column space of an A, and this basis is this basis on orthogonal basis. So is this orthogonal basis? Of course it's not, right? Because the angle between the two is not 90 degrees, right? And then intuitively, let's think about this situation of whether it is possible to find the orthogonal basis of this exact same subspace. So initially the subspace is spanned by 1, 2, 3, and 4, 5, 6, right? And then we consider this kind of plane, right? And then you guys know that the basis is not unique given the same subspace, right? So even if the same subspace is fixed, but we can find the basis as these two, and maybe these two, and then these two, and so on, right? And so we can find infinitely many sets of basis vectors given the same subspace. And then the question is whether we can find the orthogonal basis of the same subspace. So intuitively, the answer is always yes. Okay, so it means that suppose we consider this the plane spanned originally by these two vectors, which are not an orthogonal vector. But can we find the orthogonal basis for this subspace? Yes, of course, because we can just find these two vectors having a 90 degree, right? And in this case, yeah, we have no problem of finding orthogonal basis of the given, the same subspace, okay? So we will find, we will actually study how to find these orthogonal basis of a given subspace in the later chapters. Okay, but let's just understand the definition at this moment. The definition of this orthogonal basis is just the basis of a subspace that is orthogonal set. Okay, and then let's look at the next theorem, where we have the subspace W initially, and then we are given the orthogonal basis of that subspace. And then you guys know that the coordinate system with respect to our orthogonal basis. Okay. So we want to consider the situation that suppose our subspace is spanned by these two, and then so we want to represent this point, maybe this point, and then it can be represented as this, and then this point in our subspace is represented as the linear combination of these vector v1 and v2, which are our basis vectors. And then this representation, or this vector x, is c1 v1 plus c2 v2, and if v1 and v2 are basis vector of our subspace, and then if those vector x is inside of our subspace, and then we can find this c1 and c2 uniquely, right? c1 c2 exists, the solution for this c1 c2 exists, and then their values are uniquely defined because v1 and v2 are linearly independent by the definition of the basis vector, right? But what about the situation where we are given the orthogonal basis, which means that v2 and maybe v1, okay, having a 90 degree angle. Okay, so let me give an example. So W is span of 1, 2, 3, and 4, 5, 6. Then 2, 1, 0 is our vector x. Okay, and then let's just try to find out this c1 and c2. And then it is what? How do you find it? It is just solving this linear system, right? So can we directly find c1 and c2? I mean the easiest way, or the typical way of obtaining c1 and c2 is just by solving this linear system. Okay, and then so let me just explain. So what if we have the orthogonal basis of the given subspace? So let me see, 1, 2, 3, and 4, 5, this vector. So those two vectors are orthogonal to each other. And then we consider okay, so basically the problem is the subspace spanned by these two are not the same as the subspace spanned by these two. Okay, so let me make another example of first starting with orthogonal basis of 1, 2, 1, 2, maybe 1, and 2, 1, maybe negative 4. So these two are orthogonal bases, right? And then the span of these two will be the same as span of maybe 1, 2, 1, and maybe 4, 5, negative 2. Okay, so so I created this example in a way that we started from this orthogonal basis vector, and then they have the 90-degree angle because by computing the inner product between the two, they would be the same. They would be 0. But these two vectors are not having the 0 inner product value, right? But still, this vector I just created by just linearly combining these two. Okay, by just multiplying with 2 and plus, and then we obtain this vector, right? But these two vectors on the right is not the orthogonal set, but they are still valid basis of the same subspace, right? So it's like the right vector is having these two vectors having the angle different from the 90 degree, but the left basis vector is orthogonal basis of the same subspace having the 90 degree between the two vector, right? Okay, and then let's just consider the vector x as 1, -1, and -5. So I'm trying to create some example in real time. But this vector x, we want to represent C1 times 1, 2, 1, and C2 times 2, 1, negative 4. Okay, and in this case, we have to solve this linear system of having 1, 2, 1, 2, 1, negative 4 times C1 and C2, right? So we have to do some row reduction and things like that, right? But what if we want to find the coordinate or the solution with respect to a orthogonal basis vectors, okay? So in this case, the main point that I wanted to make was when computing C1 and C2, you can just find it quite easily, very easily, by just considering these two vectors. But you don't need this vector. And when you want to find C2, so when finding C2, it only involves this vector and the input vector, and that's it. And you don't need this vector at all. Okay. So let me show how to find. Okay, so it is C1 and V1 and C2 and V2, and let's just call it as U1 and U2, and U1 is U2, perpendicular to U2, or the inner product between U1 and U2 is 0. Okay, so in this case, how do you find the C1 and C2? Instead of just forming this linear system, okay. So we do this, okay. So we just do this inner product with the U1 and U2 separately applied to this equation. So in other words, let's just compute this. X dot U1 equals C1 U1 plus C2 U2 and dot U1, right? So we still need the dot here, Okay, and then C1 and U1, right? Plus C2, U1, U2, right? Okay, so here, this part will be actually gone because their inner product will be 0. Okay, and then what about C1? C1 is the coefficient, right? With respect to the first basis vector. I mean, first orthogonal basis vector, right? But obtaining this C1 is just represented as x dot U1 divided by U1, right? So that means it doesn't involve U2 at all, right? So in this example, how do you find the C1? So we just do the inner product between these two, right? Because that is corresponding to the numerator, right? And then what is the inner product? 1 and minus 2 and minus 5 minus 6. So I just did the inner product between these corresponding pairs of entries, and then I just sum them up. That gives negative 6, right? So this is just an inner product of x and U1. Okay, then, oops. What about this denominator? Denominator is just the vector length of this guy. 1 squared and 2 squared and 1 squared. Yeah, and 6. Okay, and so it is negative 1, and that is what? This guy, C1. Okay, and similarly, C2 can also be found by just doing the inner product with the x and x and the U2, and divided by the norm. I mean the U2 dot U2, right? So this is quite useful kind of property of when having orthogonal set. I mean orthogonal basis of your basis vector. Okay. Any questions so far? 네.
방금 전에 한 거,
네.
orthogonal 베이스일 때만 밑에 덧쓸 수 있는 거 아닌가요?
orthogonal basis일 때만 네 이렇게 되죠.
근데 저기 1, 2, 1이랑 4, 5 마이너스 2가 내적이 0이 되는
4, 5 마이너스 이거 어디서 넣었죠? 그러네요. 완전 잘못하고 있었네. 좋은 지적이네요. 근데 왜 이거 오른쪽 걸 썼지? 왼쪽 걸 써야죠. 여기 2, 1, 마이너스 4. Okay, sorry about the confusion, but yeah, if we replace that vector with this orthogonal version of our basis vector, and then the rest of the story will remain the same. Okay. 좋은 시작이네요. Any other questions? 네.
그 제로 벡터는 수직이 되는 건가요? 모든 벡터에서?
네. 근데 이제 제로 벡터는 이제 베이시스 벡터에는 포함은 될 수가 없어요. 왜냐면 리니얼 인디펜던트 하려면 네, 제로 벡터는 이제 포함이 될 수가 없어요. 근데 뭐 그 말은 맞아요. 제로 벡터는 이제 모든 벡터에 올서곤을 해요. 근데 보통 그 경우를 우리는 뭐 고려를 안 해요. Okay. And let me just explain the physical meaning about of the properties that we studied from this example. Okay, so so you guys remember this kind of example. So if our vectors are this guy, v1 and v2 that are not orthogonal, and then so let me just use give me 1 second. Okay. Okay, and then let's just suppose we have these two vectors, and then so these are two basis vector, and then suppose we are given some vector x over here, and then we want to find c1 corresponding to the linear combination coefficient corresponding to v1, and then how do we find it? And the process is like this, and so we basically form this guy, this parallelogram, right? And then we need to find the length of this vector, okay? The length of this vector, and then that means so here is a kind of interesting kind of notion or interesting operation that comes into play, which is called the projection. So we are given this point x, okay, and then we want to project that point into some vector, some point along the v1, okay. So basically this part or this point is along the v1, right? And then we can think of this as projecting the vector x, which is actually outside of this the line spanned by v1, into some vector on this line, and we want to find out the length of this vector, right? And then so the projection like this, done in this manner, which determines the direction of this projection. The direction of the projection is actually determined by the direction of v2. So v2 was this guy, and then it will be projected into this point. But what if we had v1 in this thing? Okay, and then what is the corresponding vector like this? And then that is like projecting this point parallel to v2, right? So we should project always along the direction or in parallel with the other vector v2, right? So the length of this vector, okay, is determined or dependent by the v2 or the other vector, right? The other vector. And then what about the orthogonal case? So if we have a 90 degree here, and then this is a v1 and v2. Suppose you are given some vector x over here, and then that means so you want to find this kind of thing, right? And then this guy is projected onto this point. But this projection is actually independent of the v2 as long as v1 and v2 are orthogonal bases, because this projection will always be 90 degree. Okay. So this is kind of a high-level intuition of being able to compute the the coefficient associated with the v1. The way of computing or obtaining the coefficient of v1 is computed only by using v1 and x, but we don't actually need v2, okay? Because we are just it is just enough to do this projection with the 90 degree angle. So this kind of thing is called the orthogonal projection. and we will kind of study it in more detail in the later parts. But yeah, please keep that in mind. So yeah, this kind of projection is always done towards the each of our basis vectors separately by just doing this projection with the 90-degree angle, which is called the orthogonal projection. Okay, so that's it for today, and today is Tuesday. So yeah, let's continue this Thursday. Okay, thank you very much.